What if we could extend the lifetime of subatomic particles? This could make it easier to study such particles by causing them to stay around longer. But the question is, how? How can we adjust the lifetime of particles with a specific half-life? Well, could it be possible? Time dilation could be applied to particles that naturally decay and have very short lifetimes, causing these particles to last much longer than they ordinarily would. You may be wondering what time dilation is. It is a variation on the dilation of time and contraction of space, effects predicted by Albert Einstein to take place when objects move close to the speed of light. An example of this is Einstein's famous twin paradox, in which a twin who travels at high speed in a rocket ages more slowly than another twin who remains on Earth. Firstly, how do we accelerate particles to travel close to the speed of light? We all know nothing travels faster than light, which has a speed of roughly 3 times 10 to the power of 8 meters per second. If we give particles enough energy, it will only move closer to the speed of light, but will not reach it. As the particle moves faster, its mass increases according to Einstein's theory of special relativity, and the only possible way it can reach this blistering speed is if it attains infinite energy. Therefore, it seems impossible for it to reach that speed. The Large Hadron Collider is a particle accelerator in Switzerland, which consists of a hollow ring with a circumference of about 18 miles, which is almost 4 miles longer than the length of Manhattan. Inside this ring is a vacuum with pressures lower than that of the surroundings of the International Space Station and is 456 degrees Fahrenheit below zero, colder than the temperatures recorded in deep space. The particle accelerator uses an electric field to pull particles to make them to move fast, or in other words, accelerate. By hooking two metal plates parallel to each other and connecting a battery, an electric field will be created between the two plates. If you connect many of these electric fields in a straight line, the particles can accelerate to speeds almost reaching that of light. However, an accelerator built this way is very weak. To solve this problem, we can use a magnetic field as well. Electric fields will make the particles go faster, whereas if you use a magnetic field, you can make the particle move in a circular path. By combining both fields, you can use a single electric field to propel the particle and use magnetic fields to guide it in a circular path to come back to the electric field and be propelled again. The beams go around the circle and gain energy. This is repeated over and over again until it reaches speeds of 99.99% of that of light. The main purpose of a Large Hadron Collider is to collide particles together moving at high speeds. The twin paradox is a thought experiment in special relativity involving identical twins. One of whom makes a journey into space in a high-speed rocket and returns home to find that the twin who remained on Earth has aged more. According to an application of time dilation and the principle of relativity, each would paradoxically find the other to have aged more slowly. This result appears puzzling because each twin sees the other twin as moving. The traveling twin's trajectory involves two different inertial frames, one for the outbound journey and one for the inbound journey, and so there is no symmetry between the space-time paths for the two twins. An example can be used to verify this. Consider a spacecraft traveling at a speed of 80% the speed of light and goes to a distant star 4 light years away. One assumption we make is that the spacecraft attains full speed upon departure. Using a simple kinematics formula of speed equals distance over time, we can rearrange the formula to get time. T equals d over v. Since the spacecraft is going and coming back, the distance will be doubled, so the new formula is now t equals 2d over v. We can calculate time taken for this journey. 1 light year is 9.46 times 10 power 15 meters, 4 light years will be 3.78 times 10 power 16 meters. Therefore, the time taken will be 2 times 4 times the value of 1 light year divided by 0.8 multiplied by the speed of light. This is approximately 10 years, according to the twin on Earth. The spacecraft's clocks will be reduced by the reciprocal of the Lorentz factor, which is a factor by which time, length, and relativistic mass change for an object while it's moving. This can be denoted by a formula, y is equals to 1 over the square root of 1 minus v squared over c squared, which can equate to dt over d capital T, where capital T is the time for an observer and t is the coordinate time. The reciprocal of this formula can be used to calculate the ratio of time difference between the twin on Earth and the twin on the spacecraft. By changing the denominator with the numerator, we get the root of 1 minus the speed of spacecraft squared divided by the speed of light squared, which is equal to d capital T over dt, showing the rate of change of time for an observer with respect to coordinate time. The root 1 minus v squared over c squared will give you the ratio. Root of 1 minus 0.8 times the speed of light squared divided by the speed of light squared is equal to 0.6. Therefore, the twin in the spacecraft will take 0.6 multiplied by 10 years to return home, which is 6 years. From the ship's perspective, the star and the Earth are moving relative to the ship at a speed v. In the rest frame, the distance between Earth and the star will be 0.6 multiplied by d, which is 0.6 times 4 light years, which is equals to 2.4 light years each for both outward and return journeys. Each half of the journey will take 2.4 divided by 0.8 multiplied by the speed of light, which is 3 years, and the return journey will take another 3 years, which is 6 years total. So, by taking Einstein's twin paradox and combining it with particles, it may be possible for particles to time travel. Sounds cool, right? Particles with a short half-life or lifetime could undergo a similar journey to increase the lifetime of certain isotopes to help scientists understand them better before they decay. Certain drugs with short half-lives could have an increased life expectancy as well. In addition, it might induce differences in the behavior of these particles.